everyone. This is the presentation video for the ICCV 2023 paper, Learning Shape Primitives via Implicit Convexity Regularization. I'm the first author of this paper, Xiaoyang Huang. This work focused on 3D primitive learning in multi-view scenarios. That is, given a set of multi-view images, we learn to decompose the objects into multiple primitive shapes. To do this, we require the primitive representation to have two abilities. First, it needs to allow neural rendering such that it could be reconstructed from multi-view images. Second, it needs to have simple geometry such that the object could be decomposed into simple primitives. To resolve it, we propose to use implicit SDF to represent convex shapes. Since SDF is widely used in neural rendering, and convex shapes are generally regarded as simple. To derive the proposed ICR, we begin with the definition of convexity. Mathematically, a shape is convex means that for arbitrary 2 points located inside the shape, the convex combination of the 2 points are also located inside the shape. If we directly apply this convexity definition to an implicit function, we will find that it is highly computation inefficient, since it requires queries of arbitrary 2 points inside the shape. So, to achieve higher efficiency, we convert the basic definition to a surface-based formulation, that is theorem 2. A shape represented by an SDF is convex means that for arbitrary 2 points that are located on the surface of the shape, the convex combination of these 2 points is located inside the shape. This formulation improves the sampling efficiency, since it only needs to care about surface points. However, there is still a drawback in this formulation, that is, imposing constraint on the output SDF values could cause serious chaining instability and oscillation, or even chaining collapse. The reason is that there is a shortcut for the SDF function to satisfy this constraint, that is to scale up the value of the final layer of the MLP. As an alternative, we propose to impose constraint on the second-order derivative. So this is the theorem 3. A shape represented by an SDF is convex means that for arbitrary 2 points, x1 and x2, located on the surface, we have positive second-order directional derivative along the direction x2 minus x1 on the convex combination of x1 and x2. It is easy to prove that theorem 3 is a sufficient condition of theorem 2. Instead of imposing constraint on output SDF value, we impose constraint on second-order directional derivative. In practice, we use finite difference to calculate derivative. A complete algorithm is presented in the paper. Here, let's have a look at the whole pipeline. We use UniSurf as our neural rendering model. Each primitive is represented by an MLP that predicts SDF and RGP feature. The final loss function is consisted of reconstruction loss and ICR. We conduct experiments on synthetic and real-world datasets. We first compare the setting of our methods and prior related works. We show qualitative and quantitative results on ShapeNet. We see that our method achieves much better reconstruction accuracy and prior primitive decomposition methods like BAENet and EMS. Our method also achieves notable semantic decomposition. Similar results are observed in Code3D dataset, which is a real-world multi-view dataset. In a Bayesian study, we remove the ICR term in our model and find that the semantics information is broken without convexity constraint. In conclusion, we propose a regularization term named Implicit Convexity Regularization for primitive decomposition. Experiments on synthetic and real-world datasets demonstrate the superiority of our method over prior art with respect to primitive simplicity, fidelity, and semantics. Thanks for listening.